All right, let's work this junk out, my guy. So let's remember our formula. So our formula, so the particular solution, so y of x is y naught plus the integral from x naught to x of f of x dx. But if we want a certain value like we have here, then y of a is y naught plus the integral from x naught to a of f of x dx. And again, I forgot to change this variable, so I don't want this to be the same as that. So we're going to say x bar, x bar, x bar, x bar.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.
All right, greetings and welcome to Differential Equations, lesson number 1. And so we're going to explore the whole course of differential equations in subsequent videos. In this first particular video, we're going to look at something called first order differential equations, where the differential equation is simply a function of x. So we're going to look at some what we call initial value problems, or IVPs, and looking for finding general solutions and particular solutions. So this is a very important course of differential equations. If you've taken calculus, you'll do some differential equations in calculus, but when you're doing differential equations in calculus, you're really just twinkling your toes in the pool of differential equations. The course is a lot more vast than the little bit that you see in calculus. In fact, you know, what we cover in just this first lesson, or in the first 2 lessons we'll cover, will be about the extent of what you'll see in calculus. And this course is gonna require about 25 lessons that we're gonna post, so 25 videos. And so, you know, almost 1/12 of those of that lesson is what's covered in calculus. So you don't really get the full deal of differential equations when you're taking calculus. But follow these videos as each lesson comes along if you're very interested in this subject, and we'll take you through the course of differential equations. So let's go ahead and start. So we want to start with the definition of what a differential equation is if you're unaware. And right now I'm using the term differential equations. To be more specific, what I'm talking about are going to be ordinary differential equations, at least for right now. Later in the course, you know, about the last 4 videos, we'll get into what are called partial differential equations. But for the bulk of the course, we're going to be dealing with ordinary differential equations. So when if I just say differential equations, for right now, I'm referring to ordinary differential equations. And an ordinary differential equations is simply an equation relating a function to its derivatives. And I say derivatives plural because it could be more than one derivative. It could be the first, the second, and third in combination. So that's why I say derivatives plural. And here we just look at some examples of some different differential equations. So we have dy by dx equals 5y. That's a differential equation used for exponential growth. And second one, we have y double prime minus 5y prime plus 15y plus 8 equals 0. That's called a second order, a linear differential equation with constant coefficients. And since I call the names, and as we go through the course, you'll get a little more familiar with what these names mean. And I just say them now when I see them. But one thing I can talk about is the order of a differential equation. So when I say a first order differential equation, that means the highest derivative in that differential equation is the first derivative. A second order, the highest derivative is the second derivative, and so on. So the order of a differential equation is what's represented by the highest derivative in the differential equation. And the last differential equation example I have there is dy by dx is e to the x minus 7 times y cubed. That one is called a first order separable differential equation. And again, these things mean something. And we're going to get into the separable differential equations in lesson 2. And when we do that, you'll get an understanding of why it's called separable. All right, so those are just examples of what they look like. And if you look at each equation, you'll see the function being y, and you'll see the differential equation or its derivative, whether it's expressed as dy by dx or y prime. All right, and so these are the different applications of differential equations. You can't talk about applied mathematics without talking about differential equations. They're ubiquitous, if you will, in terms of modeling real life physical phenomena. So just some examples, and these are just some examples of what they're used for: chemical mixtures, population dynamics, electrical circuits, acoustics, infectious disease modeling, plate tectonics, aerodynamics, and so many more. So if you want us interested in applied mathematics, or just interested in how math is utilized in the real world, differential equations is the cornerstone for that particular insight. So the main thing we want to get into today, and really the main thing, the bulk of our lessons, is going to be solving differential equations. Now, quite honestly, a lot of the differential equations you're going to encounter in a lot of situations, if you're doing real life applied mathematics, can't be solved, at least not with elementary functions. And you understand what I mean by that in a second. And there's different methods, different type of techniques, which we'll get into later in later lessons, of how to deal with those type of situations. But for the beginning of the course, when we say solving differential equations, we're going to really be able to find a solution that's represented by an elementary function. And so I'll just give an example. So a solution to a differential equation is a function that satisfies the differential equations. So again, I'm saying that the solution is a function. So in this, I'm implying that the solution can be found with an elementary function, at least for the differential equations we solve starting off. And so this is an example. So here's a differential equation: dy by dx equals 15x to the fourth. And the solution of that differential equation is 3x to the fifth plus c. And again, if it's a solution, it'll satisfy the differential equation, meaning if I plug this into the differential equation, it satisfies it. Because if I plug this in for y, this dy by dx means take the derivative of this. And that, of course, will be 15x to the fourth. Of course, c is a constant. The derivative of a constant is 0, and you'll have 15x to the fourth equals 15x to the fourth. So it satisfies the differential equation. And because the solution is arbitrary up to a constant, this is called a general solution, because it's not unique, it's general, because it's 3x to the fifth plus some constant. It could be 3x to the fifth plus 1 plus pi plus e minus 17 plus 1/2, etc. So it's what we call a general solution. And the general solution of a first order differential equation of the form dy by dx equals f of x can be found by simple integration. So if you look at this problem, and if you're familiar with integration, if I simply just integrate a 15x to the fourth, I'm going to get 3x to the fifth plus 5. So to solve a differential equation of the form that dy by dx equals f of x, and when I say of this form, that means a differential equation is a function only of x. So in our second lesson, the differential equation is going to be a function of x and y. But here, the differential equation is only a function of x. And again, we can just solve it by simple integration. So the first differential equation we're looking at, where it's a function of x, I'm going to call that 1. And its solution, the general solution to that differential equation, is what I'm calling number 2, which is just the integral of the function. Indefinite integral of the function. All right, so now we want to look at something called a IVP, initial value problem. So again, what we're looking at right now on the screen is a general solution, because again, the solution comes out with an arbitrarily constant. Well, there are some problems where they give you an initial value, and that initial value allows you to find a particular solution. So if you look at what we have here, equation 3, where dy by dx is still just a function of x, but we have this initial condition here where f of x naught equals y naught. That initial condition allows us to find a particular solution versus a general solution. So I want to go ahead and look at an example of an IVP, initial value problem. And I'm going to go ahead and solve it by hand and then make some connections of how these can be solved in general. So the example is that dy by dx equals 54 sine squared x cosine x, and it's asking me to find the particular solution to the differential equation above with initial condition f of 0 equals 2. So let's go ahead and work this out and see how this comes. All right, so here's a given problem written down. So again, this is the differential equation that I was previously mentioned. This is the initial condition, and we're going to solve the differential equation. Again, the differential equation is solved by mere integration. And what I'm going to do is, and this is something we'll talk a little bit more in lesson 2 when we deal with something called separable differential equations. But I'm going to move this dx over here just for good practice. I'm not really going to give much mentioning to why I'm doing it in this particular lesson, but just something to be consistent with what I'm going to do in lesson 2. I'm going to move the dx over here. This is why, Leibniz notation is so much more beneficial on things like this than Newton's prime notation. But so I'm just going to move this dx over. I'm going to have that dy equals 54 sine squared x cosine x dx, and I'm going to integrate like so. So here I'm integrating dy, that integral will simply be y. And here I'm integrating 54 sine squared x cosine x. And so this is a u sub problem. And so you can say that u equals sine x, where du would be cosine x dx. And so this would be 54 u squared du. You see there? So the integral of 54 u squared du. Pardon that handwriting. And so the integral of u squared is u cubed over 3. And divide 54 by 3, that'll be 18. So it's going to be 18 u cubed is going to be that integral. So it's going to be 18 sine cubed x, since u is sine x, plus some constant. All right, so that's the integral. Now we're going to use the initial condition to find the value of c. So the initial condition is this value is called, we like to call x naught, and this value we like to call y naught. And so I'm going to plug in 0 for x and 2 for y. So I'm plugging in 2 for y, and I'm going to plug in 0 for x. Well, the sine of 0 is 0, so I'm going to get c equals 2. So then the general equation, the general solution to the differential equation is 18 sine cubed x plus 2. So that's the particular solution to the differential equation. And again, you could check it by plugging this in. If you want, you would plug this in for y. You would take the derivative of y. That would be chain rule. It would be 3 times the function squared. 3 times 18 is 54 sine squared x. And then the derivative of the inside function would be sine x, and the derivative of sine x would be cosine x. And so you would get this particular guy. And so it works out perfectly. And then you can check if the initial condition works by plugging in 0 for x into the particular solution and see if you get 2 for y. And in fact, you do get 2 for y. Now, we kind of worked this out, and it wasn't a lot of work. But I want to talk about a formula that represents everything we did to find this solution. And the formula is also going to be pretty good when it comes to finding the value of the value when it comes to evaluating the particular solution at a certain value. So that's something that's going to be asked of us. In fact, that's something we'll do on our second example. So I want to break down what we did to get to this final solution. And in that, I'm going to construct a formula we can use when we see these type of differential equations. So by these type of differential equations, I'm talking about an initial value problem where dy by dx is simply a function of x. All right, so I want to break down what we did. So if you notice, so we integrated 54 sine squared x cosine x, which is, this was our f of x, if you will. If I'm saying dy by dx is a function of x, this is like our f of x here. So I make a note of a couple of things. So let's say I let big F be an antiderivative of F. And of course, where F in this case is 54 sine squared x cosine x. All right, so I'm going to let big F be an antiderivative of F. And I'm saying this guy is F right here. All right. So an antiderivative of that would be this guy. So this, what we have here, would be big F. All right, that's big F of x. Now let's look at what we did to find the value of C. So what we did to find the value of C is we plugged in y naught for y. So let me just write here what we did. So we plugged in y naught for y. So C came from the value of y naught. And we evaluated big F at the value of x naught. So we found f of x naught. Remember, we plugged in 0 for x when we were solving for C. And it was 0, so we didn't do anything with it. But normally, if I'm solving for C and this was a number other than 0, I would subtract this, to solve for C. So I'm going to say minus big F of x naught. So that was our value of C. So this is C. What we have here is C. Actually, big F plus y naught minus big F of x naught. Big F of x plus y naught minus big F of x naught. Now, I'm going to write that in a different order. I'm going to move this y naught to the front, and I'm going to say y, where y is a particular solution of the differential equation. I'm going to say y is y naught plus big F minus big F of x naught. So let's write that and make some connections. So y, I was about to write big F first, excuse me. So y is y naught plus big F of x minus big F of x naught. All right, so that's what we got for the particular solution of the differential equation. Now, remember, big F is the antiderivative of little f. So by the fundamental theorem of calculus, we know if big F is the antiderivative of little f, then we know that the integral of, say, from x naught to x of f of x dx is simply big F of x minus big F of x naught, correct? So this part on our solution can simply be written as this guy. So we can write our particular solution like this, and I'm going to write this as a function of x. I'm going to say y of x, because in the next example, I'm going to find the value at a particular value. So we can write this as y of x, where this is the solution to the differential equation, f of x, equals, with the initial condition, f of x naught equals y naught plus the integral from x naught to x of f of x dx. So this guy is a formula we can use to solve the first order differential equation, where dy by dx is a function of only x, and it has the initial condition f of x naught equals y naught. So this is a formula we can use. And again, this is a function of x. And so if they ask us to find, a certain value, find y at a certain value, say y of a, what we would do, and actually, I don't want these variables to be the same. And so we normally use a dummy variable here. I'm going to use x bar. Sometimes we put t. In the PowerPoint, I put a t there, but it variable just needs to be different from the x that's right here. So since I already did an x, I just put an x bar on the top, and you'll see that in a lot of textbooks that they use x bar. But when I pull the PowerPoint up, it's going to use a t, which is, hopefully you understand, it's no big deal. So if I want to find it for a certain value, if I want to find y at a certain value, say y of a, then all I'm going to do is plug in an a right here and evaluate this particular guy. And so that's what our second example is over, finding a certain value. But before we show that, let's display this formula. And so this is just a nice and typed out what we just kind of showed on paper. And it's just showing 3, which is the differential equation with the initial condition, and that 4 is the particular solution of that particular differential equation. And the important thing for right now is that the differential equation is just a function of x. And so later on, it will be a function of x and y, but right now it's just a function of x. And this is how we can solve it. So I want to look at another example, and this is the second example. And in this problem, if you look, it says dy by dx is negative 5 sine x over 2. And we got the initial condition that y of 4 pi equals 3. And it's asking us what is the value of y 2 pi. So it wants me to find a solution at a certain value. So let's work this problem out. And we're going to use the formula we just mentioned to work the problem out. All right, let's work this junk out, my guy. So let's remember our formula. So the particular solution, so y of x is y naught plus the integral from x naught to x of f of x dx. But if we want a certain value like we have here, then y of a is y naught plus the integral from x naught to a of f of x dx. And again, I forgot to change this variable, so I don't want this to be the same as that. So we're going to say x bar, x bar, x bar, x bar. All right, so this is what we're going to do. So let's just identify the value of a, the value of y naught, and the value of x naught. So x naught and y naught come from the initial condition. And so for this problem, x naught is 4 pi and y naught is 3. And a is the value we're trying to evaluate the function at. So in this case, a is going to be 2 pi. So according to our formula, y of 2 pi, well, that guy is going to be y naught. Y naught is 3 plus the integral from x naught. X naught is 4 pi to a. A is 2 pi of f of x. F of x is negative 5 sine x over 2 dx. All right, so that is the problem at hand. So really, we need to evaluate this definite integral. And when we evaluate this definite integral, we're simply going to add 3 to it. Problem solved. So let's see, so y of 2 pi equals, so let's integrate this guy. See what's under the hood here. So if I integrate negative 5 sine x over 2, that should give me positive 10 cosine x over 2 to be evaluated from 4 pi to 2 pi. All right, so far everything looks good. And cosine of 2 pi. So if I plug in 2 pi for x, so let me first write 3 plus. So if I plug in 2 pi for x, that's going to be 2 pi over 2, which is pi. Cosine of pi is negative 1. So that's going to be negative 1 times 10. So that's negative 10 minus, now if I plug in 4 pi for x, that's 4 pi over 2, which is 2 pi. Cosine of 2 pi is positive 1. So that's positive 10. And so that's 3 plus negative 20, or negative 17. All right, so that's going to conclude our first lesson on differential equations. Much more to come. Again, this is a very exciting and important study of mathematics. We hope you stay with us on this whole ride as we're going to go through the whole course of differential equations in about 24 or so videos. And we hope to see you next time.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.